Thank you all for coming today to engage with us on the topic of climate change. So I wanted to start off today by firstly just talking about the greenhouse effect, which is sort of the underlying principle that we have for what is driving our climate. So when the sun's rays reach the Earth, about half of the energy is either reflected back from reflective surfaces such as clouds or particles in the atmosphere, or they're absorbed into, or it's absorbed by the upper atmosphere of the Earth, and then the other half penetrates through and makes it to the Earth's surface. So, and absorbs by the Earth's surface and is re-radiated through various methods such as convection, evaporation, or infrared radiation, which is heat. Now, as that heat makes its way back out towards space, some of it is trapped by greenhouse gases, so such as water vapor, carbon dioxide, methane, nitrous oxide, ozone. These are naturally occurring molecules that are in the atmosphere that are really effective at trapping heat. And the reason for that is because they have double bonds within their molecular structure. So they're naturally occurring compounds. They've been part of Earth's atmosphere for millions of years. And because they prevent the heat from escaping, they act like an insulating blanket around Earth, or a greenhouse, which is where the term greenhouse effect came from. Their presence is really important because it allows Earth to maintain a comfortable temperature, average global temperature of about 15 degrees. And without them, we'd be sitting at about -18, which isn't very conducive for life. Now, looking at ancient gas bubbles trapped in ice, scientists have been able to observe Earth's atmosphere as far back as 800,000 years. And this is a graph of carbon dioxide. So you can see that from those ancient ice bubbles, concentrations of CO2 have actually naturally fluctuated from about 170 to about 300 parts per thousand over that time. And they go up and down approximately every 150,000 years. And when they're high, this is a warm period, and when they're low, it's an ice age. So unfortunately, since the Industrial Revolution, what has been observed is that concentrations of carbon dioxide have increased at an unprecedented rate. So especially in the last 60 years, the concentration has been rising by over 100 times what has been observed historically. And in 2013, unfortunately, we surpassed 400 parts per million for the first time in recorded history. So we are entering uncharted territory. Now, when you look at the other major greenhouse gases, such as nitrous oxide, which is the top line there, and methane, so this is carbon dioxide, which is the graph I showed you earlier, you can see that each of those gases seem to follow the same trend, albeit at different concentrations. So whenever, we observe the same peaks and troughs across those three gases. And then they all have spiked since the Industrial Revolution. And for methane, this spike is actually over 270% higher than what has been previously observed. So these are the current levels at the moment. So we're at 410 parts per million for carbon dioxide and approaching 200 parts per billion or 2,000 parts per billion for methane. Now this bottom graph here, this is a temperature profile. So similarly, by looking at the composition of the melted ice water and the isotopes that are in it, scientists can determine what the temperature of the Earth was. And you can see that this follows a very similar trend to those levels, high levels and low levels of gases, and where these areas here are areas of warming that we've observed. Now, the global temperature rise that we are seeing today has actually already started to respond to the increase in those greenhouse gases. So modern day temperature records began in 1880. And according to multiple data sets, we have risen in temperature very quickly in a very short period of time. So in 2017, we've actually, that's the third consecutive year, we've hit 1 degree warmer than the average in the late 19th century. And scientists have also agreed that if concentrations of CO2 get above or reach 450 parts per million, that we can expect to see a temperature increase that will get to 2 degrees Celsius. Now, you'll hear me talk about 2 degrees in the next couple slides quite a bit. So the reason that 2 degrees is considered significant is because it's believed to be a sort of tipping point where the most extreme effects of climate change will become unavoidable. So the frequency of extreme weather events, ice caps melting, sea level rise, widespread biodiversity loss, and even the expansion of the range of pests could all be expected to be quite extreme if we reach that 2 degrees. So, as the scientific evidence for human-caused climate change began mounting, so did the concern at the United Nations discussions. In 1990, the Intergovernmental Panel for Climate Change released its first assessment that stated that emissions resulting from human activities are substantially increasing the atmospheric concentrations of greenhouse gases. And so by 1992, in Rio, it was agreed that greenhouse gas emissions is a serious issue which requires global action to prevent the average temperature from increasing above 2 degrees. And so the UNFCCC, which is the United Nations Framework Convention for Climate Change, was formed. The first international agreement that was created was the Kyoto Protocol in 1997, and its commitment period runs from 2008 to 2020. And it's predominantly focused on reducing carbon dioxide emissions to zero. Because we're approaching 2020, discussions also began about a second international climate change agreement that would follow on from Kyoto. And so there was many discussions, and it wasn't until 2015 that we had our second international global agreement on climate change. And it covers a period of 2021 to 2030, so the next decade after Kyoto. It was actually signed by all countries, so all members of the UNFCCC signed it, which was a monumental moment. And like the Kyoto Protocol, it acknowledges that carbon dioxide emissions are the most important gas we need to focus on, but that there's now also increasingly, it acknowledges methane and nitrous oxide as increasingly important greenhouse gases. So under both the Kyoto and the Paris Agreement, countries who have signed up take up on national greenhouse gas emissions targets, and then they report on those targets. They develop domestic response or policies in accordance to those targets, and then they report on how they track towards their targets at the international level. So I guess my final point is that New Zealand's had a very long history with different governments signing up to this direction of travel while taking into consideration the values of us as an export nation. Now, the key or the primary goal of the Paris Agreement is to keep that global temperature rise from reaching 2 degrees, and actually to endeavor to keep it below 1.5 degrees. However, the other aims are to not threaten food production and to also encourage or support low emissions investments over historical investments. So things like electric vehicles over coal-fired power plants. Finally, just the Paris Agreement is also comprehensive, so it creates obligations for all countries, but accepts that not everybody will be able to do the same. It's also flexible, so each country sets its own emissions targets, and the only real obligation is for us to monitor and endeavor to achieve them. Now, if we're looking back at our temperature profile, you may recall that I mentioned that we've already reached 1 degree above late 19th century levels. So 1.5 degrees and even 2 degrees is actually not very far away. Looking at this graph, you can see that if carbon dioxide emissions continue as they have been, Earth is on course for being about 2.6 to 4.8 degrees warmer. And these three areas here are 3 possible trajectories that we might follow. So the red zone is if we continue, it assumes that we continue emitting our carbon dioxide emissions at our current levels with no efforts made to reduce them. This middle area here is assuming that we peak our emissions in 2050 and then either stabilize them or start trying to reduce them. And the blue area is assuming that emissions peak by 2020. And then we endeavor to limit, to decline them further to limit that chance of us getting to 2 degrees. Now, unfortunately, all of the pledges that have been currently made under the Paris Agreement by countries are not actually enough or sufficient enough to prevent us from reaching that modeled 2 degrees. Therefore, all parties, including New Zealand, will need to find they'll need to progressively increase their levels of ambition for their targets over time. Now, I'm not going to get into all of these because I just wanted to prompt that we do have domestic policies in place as a result of those international agreements. And so Nick will cover off the existing 2020 and the 2030 targets. Our government officials will talk about the proposed 2050 target and all of the other frameworks that come with that. So in terms of policy frameworks, we have a Climate Change Response Act that's in place. We also have our National Greenhouse Gas Inventory, which is how all of our emissions are recorded and reported internationally. We also have reference to climate change under our Resource Management Act, especially adaptation. And in terms of the tools that we have in place to help us meet those targets, we have the emissions trading scheme as the primary tool to incentivize reductions in emissions, and that's currently undergoing some review to help make the accounting for forestry a little bit smoother. And we also have local council rules and plans. So the other thing here, the Interim Climate Change Committee, the Commission, and the Zero Carbon Act will be areas that are covered in our upcoming presentations. Am I doing for time? Okay, so just get to this one. So New Zealand may be a small nation with fewer emissions compared to big industrialized countries. But however, if you combine all other small emitters, such as New Zealand, we actually add up to about 30% of total global emissions. So it is important for us smaller emitters to do our part. Under the Paris Agreement, countries were also asked to state what their target for mitigation of greenhouse gases were. And 104 countries, those in red, have specifically included agriculture as a sector that they want to reduce their emissions in. 70 of those were developing countries. Another 15 countries, the light shaded red ones, made economy-wide mitigation targets. So that includes agriculture, but they didn't specifically state it. But if carbon dioxide is the most significant gas, then why are we bothering tackling other gases such as methane and nitrous oxide from agriculture at all? Before I try to answer that question, I wanted to explain a metric that's used to compare the gases. So carbon dioxide has been and will continue to be the global priority, but there is a need to tackle the other gases, and that's because not all greenhouse gases have the same warming effects. Some gases are more effective at trapping heat than others, and each has a different lifespan in the atmosphere. So scientists developed a metric called the global warming potential, and it gives emissions of each gas a simple weighting factor and allows them to be compared against each other over a specific period of time. It's been adopted by the UNFCCC, and it's the metric that's used in both of our agreements to report on our emissions. So what it does is it looks at methane and nitrous oxide and looks at the lifespan. So for methane, for instance, it only lasts in the atmosphere about 12 years. However, it is very good at trapping heat. So it has a high ability to trap energy. And that means that when you look at the GWP over 100 years, methane is 25 times more potent than carbon dioxide at warming the atmosphere, which means that one ton of methane is the equivalent, carbon dioxide equivalent of 25 tons of carbon dioxide. And for nitrous oxide, it lasts in the atmosphere a bit longer, and it's also quite powerful, and so therefore it has 300 times the ability to trap heat, cause warming as carbon dioxide does. Now, thing I forgot to mention here is carbon dioxide is a very, very long-lived gas, which is part of the reason why it's incredibly important to get it emissions down, because it effectively lasts forever in terms of human generational time. Now, this is just illustrating what I was talking about before in the previous graphs. So the green line here is the temperature or warming impact profile of methane. So most of the warming that methane causes occurs in the first 50 years. And so you can see it's quite higher than carbon dioxide, but it does steeply fall off. And then the longer you look into the future, the less of an effect it has on the warming because it's disappearing from the atmosphere. Carbon dioxide, on the other hand, it has relatively a lower warming effect than methane, but it doesn't taper off, it doesn't disappear from the atmosphere. And so for hundreds of years, it will stay and it will have that warming effect. So the longer that you look into the future, the greater the carbon dioxide's cumulative warming effect is. So that does impact on the policies that you would want to consider when looking at these gases. So what contribution to total global warming is agriculture actually having? Recent modeling has found that globally, emissions from livestock appear to have contributed about 23% of the warming that was observed in 2010. 19% of that was attributable to methane and nitrous oxide, and the remaining 4% came from pasture conversion, so the CO2 from pasture conversion. That's globally, yes. Now, if that's projected into the future, and we're trying to figure out, well, how much may agriculture contribute in the future, that all depends on what happens with carbon dioxide. So if carbon dioxide is reduced, as countries have pledged, trying to get it down to zero, then in the future, biological emissions, so methane and nitrous oxide will continue to have a larger warming effect on our planet, which sits around that 19 degrees. However, if we don't do anything about carbon dioxide, well then of course going into the future, those gases might only have about a 5% contribution to the warming that we observe. Okay, and so we know that methane cannot be treated like carbon dioxide when it comes to deciding on long-term policy goals because it has a much shorter lifetime in the atmosphere. Therefore, its emissions don't have to go to zero. However, not acting on methane emissions at all, so if we were to stabilize them, say, at current levels, this would mean that our carbon dioxide emissions would have to be reduced much more rapidly and stringently. So instead of needing to get them down to zero by 2100, we would need to do it by 2060. So it would give us a lot less time to get it down to zero. So this doesn't take away from the fact that we need to get carbon dioxide down to zero, but it makes it more and more and more difficult, near impossible, if we don't act on the other greenhouse gas emissions. Now, if we are able to in some way to get our emissions from methane down a little bit, it effectively limits the amount of warming that happens in the short term, which means that it buys us a little bit more time to get that carbon dioxide down. So either to 2080, 2100, it depends on what we can achieve in terms of our emissions reductions in methane. So I'd just like to summarize basically by saying globally the land sector is not only vital in helping remove carbon dioxide from the atmosphere through various ways, such as trees, afforestation, carbon capture and storage, and other ways, bioenergy. But it also reduces the pressure from those non-carbon dioxide emissions. So it allows countries to achieve their ambitious Paris agreements. Here, I think that I've